Alright, so today we are looking at two different AC motors that look rather similar, but operate in very different ways. First up, we have a permanent magnet synchronous AC motor. If we look at the components here, we have the coil of wire, obviously, around a core made of laminated sheets of CRGO, that's cold rolled grain oriented silicon steel, oftentimes called electrical steel or magnetic steel. There's a little bead that holds it all together. Overall pretty simple. Again, coil of wire core, and then the end of the core, if you look here, it does not pass around the end, it just ends on either side of this shaft. Inside this shaft, this is a pump by the way, is a permanent magnet. And if we turn it over and spin the pump, you'll see that there's some resistance, and then it's going to snap around while the pole switches to the other side. So each time it does this, there's a half a rotation as the pole goes all the way to the other side. This pump also has about, but not quite, one turn of play between the pump rotor and the motor rotor. The reason for that is because this pump is made to not spin in any particular direction, and the synchronous motor, in order to actually spin and work properly, needs to be able to get up to full speed in a half a rotation. So that motor is going to be pulled around to snap to the other side in 1/120th of a second, and it needs to be able to keep spinning. That is why the pump has the extra play there, allowing the motor to get up to speed and start spinning before it catches and has the water load on it. But in this application, they don't care what direction the motor spins. And the pump is designed to not care what direction is, and the direction it goes could be completely random, just based on what part of the AC cycle it gets turned on in. There's nothing really special about the core, it just goes straight forward and back. This type of motor is also used, I've seen this motor mostly in drain pumps. This is a drain pump from a dishwasher. I've also seen this motor in drain pumps from laundry washing machines. Now, somewhat similar looking, but a bit different, is the shaded pole induction motor. Side note on the synchronous motor, those are also used in Dyson vacuum cleaners. It's what they call the digital motor. In that case, rather than being driven straight off of an AC line, of course, because it's a battery-powered thing, there's a motor controller, and that controller actually pays attention to how the rotor is spinning in order to make it spin the correct direction every time. That's why it's a digital motor, because it needs that digital control to make it spin the right direction every time. Back to this. So the shaded pole induction motor is very common. Almost any fan anywhere. This is a little desktop fan, larger ones, air filters, or your bathroom vent fan are all these shaded pole motors. Now this, you'll notice that the core goes through the coil, but it goes all the way around and continues all the way around the rotor of the motor. Secondarily, you'll notice these copper turns here. These are the shading coils, which so if you go back to your Intro to Electronics class, you may remember that an inductor, which is a coil of wire around a core, resists change in current flow. When the magnetic field passes through these coils, because these are shorted out coils, they resist the change in magnetic field similarly, just like dropping a magnet down a copper pipe. And so that causes the change in magnetic field to be slowed and delayed as it passes through and over these copper coils. Now let me turn on the microscope here. Yeah. You'll notice that there are a couple points where the core passes through the shading coils, through both 1 and then 2, to lead to the rotor at different locations. Sorry, I can't make that look any better, but you can kind of see what's going on there. So that was all right here. So again, that slows down the magnetic field change as it passes around the core. This causes the magnetic field to rotate around the core with the AC current. So even though the AC is just straight back and forth, the shading coils here, which shade or retard the magnetic field passing through, change it from straight flipping back and forth to spinning, and that's going to force the motor to spin in this direction. Now, these coils get hot. It is loss of energy. It makes the motor less efficient. But it's a very cheap way of making the motor always spin in the proper direction. And so the shading coil causes it to spin such that the fan blades always pick up air from the back and push it forward. So these are not the most efficient motors, but honestly, on a fan like this, you don't really need a whole lot of power. You just need to keep some movement going. The drain pump, on the other hand, they actually want a fair bit of power in there, so the synchronous motor here is a lot more efficient, but they can't cheaply verify and guarantee the direction it's going to spin, which is why the rest of the pump is designed to be rotationally direction agnostic. So yeah, that's 2 basic types of motors. Also, I think I mentioned there's a permanent magnet in here, whereas on this core there is not a permanent magnet. The core, the rotor, is just a block of aluminum, which may have some copper coils in it, or it may not. The main point there is that the rotating magnetic field will cause a magnetic field to build up in the rotor, which is also rotating, and because it's moving, that generates an electric current, so it acts like a transformer, and that is basically a transformer that's shorted out. So the rotating field causes a mechanical force that begins to pull the rotor in that direction. And how fast the rotor spins relative to the speed of the rotating magnetic field is the slip angle. In induction motors, as the slip angle, which is in RPM, increases, the torque goes up. On a synchronous motor, the slip angle is an absolute number of degrees difference between the permanent magnet and the core. So when the slip angle goes up, because the speed is going down and you have more of a difference, you get more current buildup in the core, which gives you higher torque. However, in order to make these more efficient where possible and reduce the power going into the shading coils, sometimes these have pretty minimal amounts of shading, and the result is that when the rotor is not spinning, there's very little rotational force and mostly a straight back and forth. So you might need the motor running at full power in order to begin spinning, in order for the spinning rotor to actually help develop the rotating magnetic field in there. Just like if you take a ball with a string with a ball on the end, you can start the ball moving in a circle, and then if you just move the top of the string straight back and forth, the ball will continue spinning in a circle, and this is similar to that. So anyway, yeah, that is the split phase induction motor and the permanent magnet AC synchronous motor. Let me know in the comments if you have any questions that I haven't answered, and I will try to do something about that. Have a good day.